Good afternoon, everyone. My name is Bill Wagner, and I'm the Senior Product Manager for CASE at Univar Solutions. I want to thank everyone for joining us for today's Industrial Coatings Spotlight Series featuring Angus Chemical Company. At Univar Solutions, we are serious about safety and start each meeting with a safety moment. Today's safety moment is on the most common phishing attacks. We all know that cyber attacks happen via email, phone, and text. These phishing scams are increasing daily. The best thing to do when in doubt is to delete the email or text. During today's session, you'll be able to submit questions via the chat box feature. The way to go about this is simple. First, click the question box as indicated in this diagram and write your question in the bottom box. Only the screen presenter will see the question and the sender will be anonymous to the other attendees. You can submit questions at any time, but we will address them at the end of the presentation. Now I'd like to introduce you to today's presenter from Angus, Mark Langille. Mark has a PhD in chemistry from Northwestern University and a BS in chemistry from Carnegie Mellon University. He holds the position of Customer Application Specialist for Paints and Coatings at Angus Chemical Company, providing technical support and formulation guidance to the paints and coatings industry. Thank you, Mark, for joining us today as we look forward to hearing about improving performance of waterborne industrial coatings with amino alcohols. With that, I'll turn it over to Mark to go over his agenda and presentation.
Thank you, Bill, and thank you everyone for joining us today. So as Bill said, I'm calling in from Angus Chemical Company. I want to tell you a little bit about how you can use our amino alcohols to improve the performance of waterborne industrial coatings. So before we get started, I just wanted to cover a brief agenda. So this is going to start with a very short introduction to the Angus product portfolio. And then what I really want to talk about is how you can use our amino alcohols as dispersants for pigments. And then following up on that, what that means for working in a waterborne direct-to-metal coating formulation. And show you some results where we used AMP as a codispersant, and also show how you can improve performance through some formulation optimizations with this chemistry. And then we'll summarize and provide some recommendations for your formulations. And so what do we do at Angus? So Angus specializes in a unique chemistry and a unique process where it starts with the reaction of propane with nitric acid. So this reaction generates a series of nitroalkanes, which they themselves can be used as solvents in a variety of coating applications. But we can also do further chemistry on those. And so we can turn those into other products, such as our amino alcohols, or other derivatives. So that's where we get our name brand Zoldine and Algaturge products from. So as you might imagine, this sort of chemical process results in a number of different products with a lot of different chemistry that can end up in a lot of different applications. But when we see its use in coatings, paints, and inks, we tend to see a lot of multifunctional benefits that arise from the interaction of these various materials with different components in a formulation. So usually when we're looking at these formulations, we're seeing improvements to not just one aspect, but to multiple, right? So in the case of what we're talking about today, we'll tell you how that helps for pigment dispersion in waterborne formulations. And so when we look across the Angus product portfolio, we have a lot of products that can be used in both water-based and solvent-based systems. So certainly amino alcohols are a very critical component of some of the additives that we have for water-based systems, and that's what we'll focus on today. But we also have some carbodiamide cross-linking chemistries that can be used in water-based systems as well. On the solvent side, this is where we have nitroparaffin solvents, some oxazoline surfactants, and as well as a moisture scavenging additive. And so all of these can provide solutions for not just water-based coatings, but also for solvent-based coatings as well. And so today I really want to focus on a unique chemistry from Angus, and that's our amino alcohol chemistry. So most people are familiar with this chemistry through materials like AMP, but we also have others. So in particular, what I'll be talking about today is also some work with AEPD and DMAMP. So all of these materials are either primary or tertiary amino alcohols, where the amine group is bonded to a tertiary carbon. So you can see the structure on the right of this slide. AMP at the top is a primary amine with one hydroxyl group functionality. AEPD is a related compound, but it has two hydroxyl group functionalities. And then DMAMP is essentially a tertiary amine equivalent to our AMP. So it's the same structure, except instead of the primary amine contains the two methyl groups to make it a tertiary amine. And these can be used for a lot of different applications in the coatings area. And the reason why that is some of the properties of these materials are different from one another, right? So if you look at this table, this is showing some of the different physical and chemical properties of these materials that arise from the chemical composition of these molecules. So a couple things I can draw your attention to is, for one, you have molecular weight. So AMP, the molecular weight of that material, is the lowest out of these three. It also has a fairly strong pKa. So the pKa of 9.7, that reflects how strong the base that material is. And so in the case of AMP, because of that low molecular weight, relatively high pKa, it's a very efficient neutralizer. So you don't need to use that much of it in order to have a strong effect on the pH of a formulation. If you look at AEPD, right, this has a different chemical composition. And what stands out in the case of AEPD is its high boiling point. So the boiling point of 283 is much higher than AMP. It's a bit of a weaker base. You'll see the pKa is around 8.8. And then if we compare that to the third material, DMAMP, this is the highest pKa material. So it's a very strong base and is used in a lot of applications where you really need a strong basicity from that material you're using. And so one common question we have with regard to a lot of our materials is, what is the VOC status of them? And so we're happy to say that AMP is the only organic amine that is considered VOC exempt by the US EPA. It is also considered VOC exempt by the Government of Canada. We also know from testing that AMP can have very low emissions in one of the California emissions testing standards. So this is related to Green Guard certification. It's also related to a couple other green label certifications. For example, LEED credits do require emissions testing of some coating materials. AEPD VOX 1000. This is a material that, although it is considered a VOC in the US, because the boiling point of this material is over 250 degrees C, it's not considered a VOC in either Europe or in China. And because the boiling point is also above 280, it is not considered a VOC for Green Seal certification purposes. We also know that this material is non-emissive in emissions testing, which can be really advantageous for formulating coatings to meet certain green standards. We have data from this, not just from the California test, but there are equivalent tests that are run in Asia and also in Europe. And we know that it's non-emissive in all of these applications tests. So today, what I want to talk about is the interaction of amino alcohols with different ingredients that are found in coatings formulations. These interactions can be very complex because these molecules can interact with so many different species and so many different materials. So on one hand, products like AMP can have very strong interactions with pigment surfaces. They can also interact with dispersing agents because a lot of the negative charges found on dispersing agents can be counterbalanced with the amine on amino alcohols. Same goes for binders. So a lot of resins are stabilized by carboxylic acids, and amines can interact with those carboxylic acids and provide stabilization. Of course, most people are familiar with the neutralization power of a molecule like AMP. Something that people might not be as familiar with is these molecules can also be used for formaldehyde scavenging purposes. So they can react with formaldehyde to form very stable oxazolidines. We also know that there's interactions with biocides. So there's a synergy between amino alcohols and registered biocides. These are products like BIT, MIT, or CMIT. We can actually enhance the performance of those registered biocides through the use of products like amino alcohols as opposed to other neutralizing options. So while there's a lot of interactions that can happen in a can of paint, the one that I want to focus on today is the interaction between amino alcohols and pigments. So the pigment dispersion process is something that I'm sure all of you on the call are quite familiar with. But essentially what you're trying to do is you're trying to take a pigment that's usually supplied as a solid powder that's in aggregate form or agglomerate form. And you need to get that into water. And so you first need to wet out those pigment surfaces. And then you apply a lot of energy through grinding. And so what this does is it breaks down the aggregates into individual primary particles. But then you need to stabilize those, right? So while you can get them to their primary particles, if you apply energy in order to keep those as their primary particles, you have to do some sort of surface functionalization. So that's the role of dispersants, where they essentially prevent the reagglomeration of those pigment particles. And this is very important for a lot of different coating properties. So many properties tied to either optical properties, mechanical properties, or whether it's even the rheological behavior are highly dependent on the particle size of your pigments in a formulation. And many of these properties can vary quite greatly. And most typically, these properties can be optimized if you optimize your dispersion of pigments. So when we consider different dispersing mechanisms or stabilization mechanisms for pigments, it really comes down to three general categories. So the first is steric stabilization. So this is the adsorption of polymers or surfactant chains onto pigment particles. What happens if you have particles that are sterically stabilized, if these particles come in contact with one another or try to come into contact with one another in solution, the steric hindrance of those polymers or surfactants will prevent the reagglomeration of two particles. And so this is one way that pigment particles can be stabilized in solution. Another way is through electrostatic stabilization. So this is through the creation of an electrical double layer, essentially, where you have ionic species that are attracted to charges that are found on the pigment particle surface. And they essentially create an electrical repulsive force between particles. And so this, again, just like steric stabilization, if you have two particles that try to come into contact with one another, they'll be repelled from one another. And so you won't get that reagglomeration. The third category is essentially just a combination of the first two. This is electrosteric stabilization. And this is the reality of most coating formulations, where it's not just one or the other. You usually have a combination of both polymers, surfactants, or ionic species adsorbed to the surface of the pigment particles. That is, together, preventing the reagglomeration of those particles. And so if you're going to have a good dispersant, really the first key property that you need to have is it needs to have a very strong interaction with those pigment surfaces. And so AMP as a material has that property. And so we demonstrate that here. So this is looking at either titanium dioxide or at a colored pigment. And so in the case of titanium dioxide, what we did was we essentially prepared a slurry with the specified weight % of AMP on pigment. So if you look at that first line, so we're looking at 0.12% weight of AMP on pigment. And then we can characterize how much of that AMP is in solution and how much of that AMP is on the particle surface. And so what we find is that in that case, 85% of the AMP is found on the particle surface and not in solution. And so as you increase the amount of AMP used in that pigment slurry, you see, a general decrease in the amount of AMP absorbed on the pigment surface. And this is a very typical response of a material that has a very strong affinity towards pigment surfaces, which is kind of shown in the cartoon that's on the top left here, where essentially we know from these experiments that if you have AMP in solution and then you introduce a pigment to that solution, much of that AMP is going to end up on that pigment surface. And it's not just for titanium dioxide. In the case of the blue pigment here, so this is the copper phthalocyanine. This is a typical blue pigment that's used. We also see very strong absorption of AMP onto that colored pigment particle surface, even more than AMP in this case, so up to 90% absorption. This is also the case for extenders as well. So this is a very similar type of experiment where on the x-axis we have the concentration of AMP that was introduced as a weight percent on pigment, and then the determined concentration of AMP that's absorbed onto the particle surface. And so we have this plot for, if you start sort of at the bottom, we look at a calcium carbonate. The line in red is looking at a TiO2, and some of these blue lines correspond to either like a delaminated clay or a kaolin clay. And so what we see in all of these cases is we see an adsorption of AMP onto the extender particle surface. So for example, if you look at 1% AMP on pigment weight in your slurry, we're seeing about 10% of that is found on the surface of calcium carbonate, 15% on TiO2, and it increases from there when you start to look at some of the clays. And so this, again, is a very typical response for a material that has a very strong absorption to particle surfaces. And you can measure this or quantify this effect in a coating formulation by looking at a dispersant demand curve. And so these dispersant demand curves are generated by taking a grind of pigments or just TiO2 and slowly adding or introducing your dispersing agent. And so plotted on the x-axis is the dispersant dosage on TiO2 as a weight percent on solids. And then plotted on the y-axis is viscosity. So as you break down those particles from their agglomerates into their primary particles, there's a correlation there, not just with the particle size, but also with the viscosity. So a decrease in viscosity correlates to a smaller particle size in your slurry or your grind. And so what we see is for a typical polyacrylate dispersant, that's the curve in dark blue. So as we continue to add this dispersant to that grind, we see the viscosity decrease, and we see a minimum viscosity, which usually indicates the best quality grind you can achieve at around 0.5% of that dispersant on pigment solids. If you compare that to the case of AMP, which is shown in the red curve, what's obvious is that just a little bit of AMP can have a pretty dramatic effect on the viscosity, where we're seeing it doesn't take very much AMP at all to really start to drop that viscosity of that grind. You can also consider the case where you combine both the polymeric dispersant and a product like AMP. And so that's that curve in purple here, where we started with an addition of 0.1 weight percent of AMP, and then we started to titrate in the polyacrylate dispersant. And so we're already starting to get a pretty low viscosity of this grind. What we do notice is that if you keep adding the polyacrylate dispersant, your viscosity does start to creep up a little bit more, indicating that you might not have the best quality grind at those levels. And so really, the best case scenario that we found is the case of this light blue line, where we pre-added 0.1 weight percent of the polyacrylate dispersant and then titrated in AMP. And so we get a very low viscosity and a very low dosage of AMP in the polyacrylate dispersant. So really the ideal scenario to get a really high quality dispersion for this grind was found to use 0.1% of the polyacrylate dispersant with around 0.1% of AMP, which minimizes the viscosity of that grind, which means that you're getting a very good particle size distribution in it. And we know this is the case with many different dispersants. And it's also not just the case with AMP. So very similar experiments can be done with either AEPD or DMAMP. And so what I'm showing here is some dispersant demand curves using AEPD, just as an example, and also looking at it across a number of different dispersing agents. So this list of dispersing agents covers a wide range of different dispersing technologies, whether it's a polyphosphate or a hydrophilic copolymer type dispersant, and also different neutralizing agents. So whether it's a sodium salt or an ammonium salt of that dispersing agent. But regardless of the dispersant chemistry, what we see is that the titrations of just the dispersing agent itself, which are in light gray, compared to using 0.3% of AEPD, we see much lower viscosities and much better quality grinds achieved with using AEPD as an amino alcohol to help co-disperse these dispersants. And we see that regardless of dispersant chemistry. So this can also help you from a practical standpoint, because it can help reduce grinding time. So this is a graph that looks at the dispersing time versus the average particle size. And so what we find that if we're using sodium hydroxide as a neutralizer in this grind, we see that there's a general slope downward as the particle size decreases with time, which is what you would expect. And so after about 40 minutes or so, that's when you really achieve your minimum particle size from that grind. But what we find is that if you run this dispersant grind with either AMP or AEPD, you're essentially getting your minimum particle size grind after only 10 minutes, which is significantly less time than with the sodium hydroxide as a dispersant. This also influences potentially energy consumption. So the grinding process is very energy intensive. And so there's actual potential energy savings that can be gained by using amino alcohols as dispersing agents. And so there's a lot of data on this graph, but if I just draw your attention to a couple of these different data points, this is plotting essentially the power draw on a disperser for a couple different grinds. So the data in black is basically looking at an ammonia neutralized system, where the data in gray is a sodium hydroxide neutralized system. But if you take a look at these other curves, so either the blue, which is AMP95, green, AEPD, or purple, which is DMAMP, you start to see that the power draw on this Cowles disperser is lower. And so there's actually a potential to save energy by about between 10 to 20%. So this can really add up if you're making multiple different batches of grinds and you're really spending a lot of time doing this in your production. And so what does this all mean? There's a lot of challenges in waterborne industrial coatings that I'm sure you're all very, very familiar with. A couple of them that certainly come to mind for a lot of us are corrosion resistance, adhesion, weatherability, or UV protection. There's also a lot of concerns around aesthetics, right? So you want to make sure that the gloss is correct, the color is correct, you have good hardness from direct to metal type of waterborne coating. You're also looking at durability. You want to make sure that your coatings last a long time so they have very good service life. They also need to have certain resistance to whether it's water, chemicals, being cleaned. You also want to make sure that there's application robustness, right? So especially for coatings that are applied outdoors, you want to make sure that even if it's a humid day, you're still getting good film formation. Or even if it's applied shortly before a rainfall, that coating is still going to adhere and cure appropriately to that metal substrate. And pigment dispersions have a very important influence on a lot of these properties. And so a good quality pigment dispersion can really provide, it's not just a more efficient use of the pigments, but it can also provide better optical properties, which can lead to better aesthetics. It can also lead to better barrier properties, which can improve things like corrosion resistance and water resistance. So the pigment dispersion step is a really critical step for making sure that you're able to hit these different performance features in waterborne industrial coatings. And so we took a look at this. We did this through a waterborne acrylic direct to metal formulation. This is a very standard formulation that we used. This happened to be based on the Main Coat 4950 resin from Dow. It's essentially a white gloss direct to metal coating formulation at around 17.5% pigment volume concentration, 36% volume solids. This is a less than 50 gram per liter VOC formulation. This binder in particular is a type of latex that is pigment aphinic, and so it can form latex pigment composite particles. We used sodium nitrate as our flash rust inhibitor, and we also used a Dowanol DPNB as our coalescing agent. This is a slower evaporating solvent. Our pH target for this formulation was around 9.2, Ku viscosity target around 100, and ICI around 1.2. And so how we went about taking a look at this formulation is we wanted to evaluate the use of AMP95 as a codispersant in the grind. And we looked at replacing 17, 30, and 50% of the existing dispersant with AMP95. And it's really critical, I think, how we did this. So we replaced the dispersant active on pigment solids. So in this case, our initial dispersant, the Tamil 681, is 35% active. We treated the AMP95 as 95% active. And so if you look at this on an active on pigment solids, this is down at the table here. So our original formulation essentially contained 1.5% of Tamil 681 on pigment solids and no AMP95. If we removed 17% of that dispersant, we are now at 1.25% of the Tamil 681 on pigment solids. And we introduced 0.25% on pigment solids of AMP95. And we continued this through up to 50% reduction in the primary dispersant. Most people aren't used to thinking about using AMP95 in terms of an active on pigment solids, so we can convert this to an as supplied amount on total formulation weight. And so in this case, we're essentially looking at 0, 0.05, 0.1, and 0.16% weight of AMP95 on total formulation weight. And this is how we'll refer to these different formulations in the next couple of slides. But what's also important is that we're only evaluating AMP as a codispersant. To hit our pH target, we still used ammonia. So when you use AMP, it will have an effect on the pH, but when we made our final pH adjustment, we're just using ammonia in the letdown. And so what did we observe with some of these different paints? So one of our first observations was that we saw that the paints that contained AMP showed improved viscosity stability. So this is a plot looking at the viscosity, the Ku viscosity, either overnight after the paint was made, 1 week, 1 month, and 4 months of room temperature storage. And so what we see immediately is that we don't see such a large viscosity rise overnight in the paints that contain AMP, especially with a latex like this, which is capable of forming latex pigment composite particles. That has a very significant influence on viscosity. And so the ability of AMP to really reduce that viscosity rise seen over time can be very useful for these types of formulations. We also noticed that after a longer term stability testing, that we tended to get a little bit of soft packing of the pigment particles and settling found in our formulation, our control formulation. But that wasn't the case when we were using AMP. So AMP really prevented not just the viscosity rise seen in this formulation, but also in preventing some of the settling and soft packing of the pigment over time. We also saw that AMP could improve the contrast ratio and the gloss of these formulations. So on the left is a plot of the AMP percentage on total formulation weight by contrast ratio. And so our initial control formulation had a contrast ratio of around 97%. But in the case of when we were using AMP, in all cases, we saw an improvement to the contrast ratio. The best improvement happened to be with 0.1% AMP on total formulation weight, where our contrast ratio increased to 97.4%. We also saw improvements to gloss. So this is the graph on the right, and we're showing both the 20-degree and 60-degree gloss. So the 60-degree gloss is in blue, corresponds to the y-axis on the right, and the 20-degree gloss is in the dark yellow, which corresponds to the y-axis on the left. But in both cases, we saw an improvement in the gloss with higher use levels of AMP in the grind. And so in the case of the 20-degree gloss, we're seeing an improvement of around 8 units, which is noticeable. And hopefully I can get to my next slide here. I think it's thinking about it. Maybe it will respond in a second here. All right, here we go. And now it's jumping ahead. So, well, the next topic I wanted to talk about was, I think the slides will catch up to us in a second here. But it's one thing to improve gloss, but you want to make sure that that gloss is retained, especially if that coating is exposed to the weather. And so what we looked at was gloss retention when these coatings were exposed to continuous UV exposure. And so our control sample here is shown in yellow, and this was the 0% AMP. That has the lowest gloss values, but the gloss retention is fairly consistent over time. There's an increase after the first week of UV exposure, but it maintains itself over the subsequent 6 weeks. But what we see is with increasing amounts of AMP, we really see a strong increase in the gloss. Again, we still see an increase after that first week of UV exposure, but we also see that it's stable over time. So AMP can not only just increase the gloss, but it will make sure that it's stable. The other test that we looked at was corrosion resistance, which you know is very important. And so this was following standard ASTM B117 testing conditions. So this was about a 2 mil dry film thickness on steel panels that were vertically scribed. These are showing results after about 336 hours. And so what we can see is that if you look at the sample, the control sample, there's quite a lot of blistering that occurs. And this blistering and corrosion is reduced as you use more AMP. And so this shows that when you use AMP in the grind, it can be used to improve your corrosion resistance of some of these waterborne direct metal formulations. We also looked at a couple other properties. So coating hardness. This is something that we monitored over time. So after 1 day of drying and then up to 28 days of drying. So you can see the hardness development in this formulation. And what we find is that there's really not a huge difference between some of these different samples. So they all track pretty closely with one another, where we see an improvement to the coating hardness, certainly between the first day and 1 week dry times. And then there's just a very slow increase up to around 28 days. But between different samples, we're getting fairly similar coating hardness values. Usually the samples with AMP are either equivalent or around 1 to 2 seconds softer than the control formulation. So I would expect that if you use AMP concentrations that are too high, you would see a more significant effect on your coating hardness. But in the case of this formulation, we're not seeing very significant effects at the levels of AMP that were used. Early water resistance is another critical test. And so we did check that with this formulation. So the test method was essentially a 3 mil wet drawdown on aluminum panels. And this was dried for precisely 2 hours at room temperature conditions. And then they're submerged under tap water. We also measured the weight of these panels before and after submersion to calculate a % water uptake. And so what we see in the images of these panels and also in the % water uptake is that there's not a huge change compared to the control formulation. You can certainly see that just in the panels themselves, their control has no evidence of blistering. There's a little bit of blistering in the sample with 0.05% AMP, but it's pretty minimal, especially for 0.1 and 0.16% AMP on total formulation weight. The water uptake is around 20%, which is similar between the control and the samples with AMP. What we do notice, however, is I did just want to point out that if your AMP concentration is too high, you can find negative effects, right? So on the far right is an example showing where we use 0.4% AMP on total formulation weight. And for this particular formulation, that was a bit too much and started to show some detrimental effects to early water sensitivity. But if we stuck within the levels of AMP that we used here to be used as a co-dispersion in the grind, we really didn't see too many negative effects, which is great. So what are the reasons for some of these improvements that we're seeing? So really, a lot of this comes down to getting a better quality pigment dispersion. So in the case of our control formulation, where we're not using AMP as a co-dispersant, right? If you have a poor quality dispersion of your particles, a lot of that incoming light is not going to have as many opportunities as it could to be scattered. And so you're going to get lower opacity. This can also affect and reduce your gloss. Also, if you have a lot of pigment-pigment interactions, those interfaces can be very sensitive to water. And so you can get more water uptake and also more ion transport, which leads to worse corrosion resistance. In the case of when we're using AMP as a co-dispersant, we believe we're getting a much better distribution of our pigments into that coating formulation. And so we're getting better opacity, better gloss, and this is coming through more scattered light because your pigments are better dispersed. This can also affect your barrier properties. So we're seeing improvements to corrosion resistance, and we're not seeing any loss to our water resistance, especially our early water resistance. So a lot of these properties can really be tied back to the quality of that dispersion. But AMP also has some other unique properties, right? This is really getting at that multifunctionality. So AMP also has wetting properties, which can be really useful as a formulating tool. So what I'm showing here is drawdowns. So images that were taken of drawdowns that were still wet. So this is wet film images. On the left is our control. So our original formulation had fairly decent surface characteristics. So there are very few surface defects that we saw. But what we noticed is that if we reduced our surfactant concentration by about 25%, you really start to see a lot of defects, right? So that surfactant was really necessary to eliminate a lot of the craters and the pinholes that we see when we reduce that surfactant. But if we take that same formulation with the reduced level of surfactant and we reformulate it with the 0.1% AMP along with a 30% reduction in dispersant, we see very few surface defects. So AMP can really help you formulate to reduce the level of surfactants in this, this particular formulation. And you can still get a very good quality film surface. The other interesting aspects that we see as a result of this is that we did some salt submersion resistance testing. So this was testing where we essentially applied the coating onto a steel panel, just like we would for the B117 corrosion test. But instead of using a salt spray, we simply just submerged these panels into a 35 gram per liter sodium chloride salt solution. This is showing results after 336 hours of salt submersion. So what you see on the control is that there's a lot of blistering and a lot of corrosion that's occurring. In the case of when we took the control formulation and reduced the surfactant by 25%, we start to see an improvement to this. But the best improvement was really seen when we took our reformulated formulation, where we used AMP as a co-dispersant, removed some of the dispersant, and also kept that surfactant concentration low. That really helped to improve the salt submersion resistance of this coating. We also see that play out in the traditional ASTM B117 salt spray testing. So in the results, we have, you see a lot of blistering in our control formulation. The same is true for the sample where we reduce the surfactant. But if you compare this to our reformulated sample, there's a significant improvement in the corrosion resistance that we're seeing with these formulation changes. Another potential benefit of AMP in this formulation is that we believe that AMP can contribute to the flash rust resistance of the coating. And so what we did here was we took a 1.5 mil wet film thickness drawdown that was on a steel panel, but rather than curing this at room temperature conditions, we cured this under in a controlled temperature and humidity chamber. So we looked at 25 degrees C and 90% relative humidity. So this is a very, very harsh curing condition for these formulations. And so all of these formulations that were cured under that condition showed evidence of flash rusting. But what we noticed was that the flash rusting was much less for samples that contained AMP. And so we quantified that by looking at a delta E, so a difference in color between those samples that showed a general flash rusting. So the iron from those samples generated a more reddish brown color in the coating that could be picked up using a color meter. And we compared that to similar samples that were dried under room temperature conditions. And so we see that there's less of a color change, less flash rusting associated with higher use levels of AMP. So there's also potential opportunities to optimize or reduce the amount of flash rust inhibitor used in the formulation that contains AMP as a codispersant. So in summary of the benefits that we're seeing with the use of AMP in these waterborne direct to metal coating formulations, we see improvements to contrast ratio and gloss, very good gloss retention. We also see improvements to paint stability and corrosion resistance. And at the same time, fairly minimal impacts on other film properties, such as film hardness or early water resistance. And this is really all coming from getting a better quality pigment dispersion using AMP as a codispersant. These materials are very strongly adsorbed to pigment particle surfaces, and they can really do a lot to help improve a lot of the properties of these formulations. There's also opportunities to adjust other formulation parameters as well. So as we mentioned, you can, it's best to do this by using AMP in place of a regular polymeric dispersant. If you're reducing your dispersant level, there can also be opportunities to reduce your defoamer level. We also showed that you can reduce your surfactant level, in this case by about 25%, and still get some very nice improvements to corrosion resistance or salt soaking resistance. There's also potential opportunities to reduce the level of flash rust inhibitor, which can have very similar consequences towards coating improvements. And so based on this data set that we have, our starting point recommendation will be to use 0.1% of AMP95 on total formulation weight. And you can use that to replace 30 to 50% of the existing dispersant. And that should yield some improvements to a lot of these coating properties that are really critical to waterborne industrial coatings. So before we turn it over for questions, I did just want to mention that today we had an opportunity to talk about our amino alcohol products, which are really great in waterborne coating systems, but we also have some solutions for pigment wetting in solvent-based systems. So Nipar S10 is a nitroparaffin solvent, which has the ability to improve pigment wetting. Alcaturge E is an oxazoline surfactant, which can really provide excellent pigment wetting in solvent-based systems, particularly effective with materials like carbon black. We also have Zoldyne MS Plus, which is a moisture scavenger that can be used to remove water from pigment surfaces, particularly when used in a 2K polyurethane type system. So these are other types of pigment wetting solutions that Angus has. But with that, I just want to thank you very much for your attention. And I think I'll turn it over to Bill now.
Great, thanks, Mark. Thank you, Mark, for a great presentation. At this time, we'll now open it up to questions. So as a reminder, you can submit questions via the chat box feature. First, click the question box as indicated in this diagram and write your question in the bottom of the box. Only the presenter will be able to see the question, and the sender will be anonymous to the other attendees. All right, so I think I tried to jump in there and the slide was still going. This is Bill Wagner. Thanks again, Mark. We do have a question. The first question to be offered today is, what can be added around the use of AMP95 in a waterborne system where the customer is dispersing titanium dioxide? How can you optimize the use of AMP95 to reduce TiO2 to improve dispersing of the pigment without sacrificing opacity?
Yeah, so there's a couple comments I can mention. So the approach that we took in this work was to essentially use AMP to help improve the pigment dispersion, which in turn improves the opacity of the formulation. But the second approach you could take would be to try and match the opacity of a given formulation by reducing the amount of TiO2. So you could take advantage of the increase in opacity that AMP can provide and reduce your TiO2. So how you could run that experiment would essentially be take a formulation that you have used AMP as a codispersant, and then compare that formulation to one where you've removed, say, 5% of your TiO2 and 10% of your TiO2, and then you can try and match the opacity of the original formulation. And so doing that experiment would tell you how much TiO2 you could remove from your formulation, but still matching opacity. So that's definitely a formulation strategy that can be used with AMP.
Okay, yeah, that's helpful. Makes sense. So a somewhat similar question, Mark. Have you ever studied whether AMP95 would assist in the dispersion of silica containing pigments?
You know, we haven't looked at pure silica pigments, but we do know from our experiments with titanium dioxide and also with some clays, and a lot of those have, in the case of titanium dioxide, they have silica treatment on the surface, and a lot of the clays will naturally contain a lot of silica. And AMP is quite effective as a dispersant. You know, so one of the mechanisms that drives the interaction between AMP and pigments is it's an electrostatic interaction, right? So AMP has an amine, which can be positively charged. And so it's going to interact very strongly with other negatively charged species. So like a silicon dioxide or a TiO2, those can have a lot of negative surface charges on them. And so AMP works very well in those formulations where you have those opposite charges essentially attracting one another. So yes, essentially, I think that we would see a pretty good performance from silica particles.
Okay, very good. Another question's come in, pertains to DMAMP and whether or not you've ever evaluated it as a PU catalyst, being the nature of it is a high pKa tertiary amine with OH functional species. It appears that it could be a very effective catalyst in polyurethane foam systems.
Yeah, no, that's a great question. My answer is yes. So to go to more detail, we haven't run some specific studies ourselves looking at that, but you know, theoretically, I think that DMAMP is a really great candidate for that application because you know, one, you have tertiary amine, which can act as a catalyst for polyurethane systems. It also has some unique solubility characteristics, right? So it's miscible in both water, but also in a lot of solvents, which can really help with compatibility with this particular tertiary amine in various systems. It also has that OH functionality, that hydroxyl functionality. So if you're concerned about emissions of amines from a cured polyurethane system, then I would expect that that hydroxyl group can react into the backbone of the polyurethane and help reduce some of the emissions. So this is actually an area where we're trying to do some more work in ourselves. So definitely stay tuned. But this is definitely a feasible application of DMAMP.
Okay. I think we've got time for at least one or two more questions. So following up on that one, this question surrounds some of the data that you presented and is specific to the charts around the viscosity and I think the degree of dispersion and the time to achieve that dispersion. The question really is around the data points and were they generated from mill grinds or Cal's dispersion method?
Yeah, so these were generated from Cal's dispersion methods. We also know that we've done some work with ink formulations that were done in more of a mill grind type of system, and we also see improvements in there as well. So, one area that we didn't talk in great detail about today is organic pigments. Organic pigments face many of the same challenges as something like a titanium dioxide or inorganic material. And we do see some very good results with using AMP as a codispersant for these organic pigments. So it studied a couple different colors and a couple different pigments, but overall, I would say that the results are very similar to what we find with TiO2. Usually in an organic pigment system, if you're thinking of making like a pigment paste, for instance, you do have to use much higher levels of your dispersant. So in a pigment paste, for instance, you might start out with more around 10% AMP on pigment weight, for instance, to make sure you can break down those particles well enough. But yes, it can be used in many different sort of pigment grinding systems. We've seen it can be very effective.
Okay, and I think we have one final question, which is really a follow-up to that. Is in the other products that you highlighted today, have you done the comparison between AMP95 and those materials?
Yeah, so we haven't done yet. This is still ongoing work in this particular direct-to-metal coating formulation we have, but we have a lot of data coming from more architectural type formulations, and I think a lot of that is transferable knowledge, right? So in the case of DMAMP, we know that that is, because it's such a strong base, it can sometimes be even more effective than AMP at dispersing pigments. The trade-off is that it does have a higher molecular weight. So sometimes on a per pound basis, you might actually be able to get away with less AMP. But it is a very good dispersant for pigments. So if you recall on the slide where we were looking at the Cowles disperser output, or I should say the energy consumption of the disperser, DMAMP actually had the lowest viscosity for that grind. And so it can work very well in these formulations. In the case of AEPD, it's not quite as good at dispersing pigments as AMP. And what I mean by that is you need to use slightly more AEPD to get the same dispersing ability. But what we find a lot of uses for is that because it has that non-emissive characteristic from the California emissions test, as well as the emissions tests for Europe and Asia, that's a really helpful tool to try and achieve those green certifications. It's also used for low odor applications. So AMP already has a fairly mild odor to it, but if you're really trying to make an odorless coating formulation, AEPD is usually our choice. You'll notice a big difference, I think. And especially, we know we have a lot of experience working with formulations from Europe, where they're really trying to push the odor profile of the paint down to, 0. And a lot of those formulations can do that using AEPD. The other benefit of AEPD that we see in formulations comes down to the biocidal synergy. So this is an interaction between amino alcohols and biocides like MIT, BIT, or CMIT, where you can actually use AMP to help extend the shelf life of a paint when it's paired with a registered biocide. And so you can actually extend the shelf life of these formulations if they're formulated with amino alcohols. We know from our testing that AEPD in particular does extremely well in that performance property. And so that's another reason why a lot of people have interest in AEPD.
All right. Well, thank you again, Mark, for that, answering to those questions. Good questions that were submitted. Again, if anyone is interested in samples or have questions about any of the materials that Mark highlighted today or anything in the Angus portfolio, you can contact your local Univar account manager, reach out to your customer service representative, or call the 800 number listed, or visit the website also listed there. Also want to remind you of the upcoming webinar series that we're putting on. Please do plan on joining future presentations as your schedule might permit. Just want to thank Mark again for his time and the material that was presented, and for everyone joining. Certainly hope to see everyone on a future seminar. Have a great afternoon and balance of your week. Thank you.